students, we are going to explain you about basic electrical engineering, and soon my friends will join this video to explain you about Kirchhoff voltage law, Kirchhoff's current law, Thevenin's and Norton's theorem, and the last one is operational amplifier. First, I'm going to explain about parallel circuits. So, as you can see here, this is the parallel circuit. So, parallel circuit is where you put the resistors on the same exact node, like this one and this one. On this project board, there are supplies, and you can put the supplies on this positive, or you can use the provided supply, this 15 volt. If you put the wire on the supply positive, it means you have to connect this project board to a computer so you can change the voltage to whatever you want. But if you want 15 volt, it's provided here, so you just have to put it right here. There are alphabets, this A, B, C, D, E. It means that all of these holes are connected horizontally, but this group and this group, this group and this group is not connected horizontally because they are separated by this spine. And these holes, this one, and this one, are connected vertically, and it's not connected with this. Second, I'm going to explain about series circuit. So series circuit is where you put the resistors like this. This is the resistors connected to a different node. Like this one is different with this, but these ones are connected to the same node. And this one, so this is the series connection. And like in parallel circuits, you have to put a wire to the supply and a wire to the ground.
Hello, my name is Leticia, and today I will explain you about KVL and KCL, or Kirchhoff voltage law and Kirchhoff current law. Okay, first I will explain you about KVL. KVL have to be put it in parallel circuit just like this. So, first you have to turn on your NI outputs to be able to measure the voltage across the circuit. To measure the voltage, you can use a multimeter, just like here. Adjust this into voltage, just like this. Okay. To measure it, put the negative, which is the black one, right here, and the positive, which is the red one, in here. And then the multimeter will show you what voltage across the circuit. To measure the current in KCL, first you have to unplug the cable, the power supply cable, to another node. You can put it here, and then just measure it. To measure the current in multimeter, you have to unplug this red one from here to put it here, right here. There is a few different options to measure ampere. Like in here, this is for ampere, this is for this is for milliampere, and this is for microampere. But for these two, you have to put it here, while ampere, you put it this in here. To measure the resistor in series, you can just put it here and here, just like that. And to verify it, using the equation, which is R1 plus R2. To measure the resistor using multimeter, you can put it wherever you want and put it here and here. You can also measure the resistor by using their color, by counting their color. And to measure the resistor in parallel circuit, you can just put it like it normally would, here and here. And to verify it, you can count by the equation of 1 per Rp equals to 1 per R1, which is resistor 1, plus 1 per R2, which is resistor 2. So in this resistor, the first one is brown and the second one is black, so this 2 is 10, and the B3 is also brown, so you can put this to the equation and the result will be 100. So this resistor is 100.
Hello, my name is Andrew, and today I'll be explaining Thevenin's theorem. So what exactly is Thevenin's theorem? Thevenin's theorem is a technique of simplifying a complex circuit by placing a single voltage source and connect it in a series circuit with a resistance and a reference load. And through this, we need to find the voltage Thevenin and the resistance Thevenin resistance, forgive me. But we also need to find a reference load as our basic exactly is a Thevenin's theorem. So as far as it may concerns, as far as there is load, we believe that we can always simplify a complex circuit by replacing the circuit with a single voltage source and a single resistor, and connecting all three components in one series circuit. Let me give you an example. Okay, so let's say that we want to simplify this circuit. See? Looks easy and complex at the same time. So let's say that we want to take R3 as our load. First, we have to measure the voltage across I3 in order to confirm the theorem is correct. 3 volts. Let's remove the load and move to the next circuit. In here, as you can see, we already removed the R3 and we only have 2 resistors and a much simpler circuit. So what we're going to do now is that we're going to find the voltage Thevenin. In order to find the voltage Thevenin, we must assume that the current never flows to the R3, and therefore this circuit is but a mere series circuit. And we need to find the voltage across the R5, because in the original circuit is a parallel circuit, and therefore the voltage in R2 is equal to R3 and therefore equals to R5. And as you can see here, the voltage across R5 is 6 volts, and therefore it is our voltage Thevenin. Okay, so next we need to find the Thevenin resistance. So basically, how to find the Thevenin resistance is that we need to see the reference back to our original circuit. Okay. As you can see, we need to find the resistance from this node and this node. So therefore, we need to connect this resistance and this resistor and this resistor in parallel. And in order to do so, we need to also remove any current or voltage source. So as you can see here, I reconnected both resistor in parallel, and let's see the total resistance. So it's 10 kilo ohm, so therefore that is our Thevenin resistance. Okay, and last but not least, we proceed to the final step, which is combining both the voltage Thevenin and the resistance Thevenin and our reference load. So as you can see here, we have our voltage Thevenin, and that's our resistance Thevenin, and that's our load. Okay, so now we need to check the voltage across our load, which is 3 volts, and that is the same as our first initial circuit. So therefore, we can confirm that the Thevenin's theorem does apply in this circuit.
Hello, my name is Vera. Today I want to present about Norton theorem. What is Norton? Norton is exactly same with Thevenin, which make the complex circuit to more simpler. In Norton, we want to measure the current, and in Norton, the current is parallel with the resistance. So this is the sample of the circuit. This is the initial circuit. The current is 3 microampere and the voltage is 3. And this is you want to measure the voltage Thevenin. The voltage Thevenin is 6. And this is the resistance Norton. Resistance Norton is 10 kilo ohm. And this is we want to measure the current Norton. Current is 3 microampere and the voltage is 3. This is the comparison with the Thevenin circuit. The result is same with the initial.
Hi, my name is Daniel and I'm going to present you about op-amps. This little thing is op-amps. It has 8 legs and here is the function. This is op-amps and this is the inside of it. Op-amps have 8 pins with each different function. The first pin is offset null, we don't use it now. The second one inverting, third non-inverting, 4 and 7 is for the limitation, 6 is the output, and 5th the same as 1, we don't use it now, and 8 is no connection, we don't use it. This is an open loop. In this experiment, I'm going to present to you about the inverting and non-inverting function of op-amps. The triangle one is the op-amps. The plus one is the non-inverting input and the minus one is the inverting input. You can see from this circuit, the non-inverting one is bigger than the inverting input. So these are the results. It amplifies both of the input as a positive result. But let's see when we change the non-inverting input to a lower input, then the inverting input. It will amplify as an inverting result. These are the inverting amplifier. You can see the input is 1 volt. The first resistance is 1 kilo ohm. The second resistance is 10 kilo ohm. And look when I start the simulation. It becomes minus 9.987 volt. And here is why. This is the inverting amplifier formula, and we can see from this the amplifying system is minus R2 per R1. Here are the non-inverting amplifier formula. As you can see here, the formula system is R2 per R1, so it will be a positive result. This is the non-inverting amplifier. The input are located in the non-inverting pin. It has 1 voltage in it, and the first resistance is 1 kilo ohm. The second resistance is 10 kilo ohms. And here is the result. 11.012 volt. And here are the results. See, it's positive. It's not inverting.